Welcome to science class. Today we are going to begin a unit on historical geology. That is, the branch of geology that utilizes principles and techniques to reconstruct and understand the geologic history of Earth. Earth is composed of several natural systems, and all of its features are produced from those systems. Once you understand this, you can view geology in a brand new way. Layers of rock strata and the fossils they contain are like the pages and chapters in a book. They tell you a story from the past. Understand that this was a very important change in scientific thinking. Until the 1800s, the vast majority of everyone, including scientists, assumed the world was only a few thousand years old. They thought there was nothing the geologic record could tell them about the past because all of it had been created recently. In the first two videos of this unit, we are going to investigate how we learned that previous statement is untrue. First, by taking a look at rock strata and interpreting how layers are deposited, then by examining the fossil record. Our goal today is to jump into the history of early modern geology and to see how we came up with the ideas that allowed us to be able to peer into Earth's history by looking at rock strata. Let's get started. Let's pretend we live in another time. 500 years ago sounds fine. You look around the world and you ask yourself, how long has all of this been here? You understand that, of course, that tree right there hasn't always been there. It grew. But what about the idea of a time when trees didn't exist? Or how about that mountain? Nobody's ever witnessed a mountain being created. Are they created? Or have mountains always existed? And what about people? What reason would you have to think that we haven't always been around? Well, if you just sat there and thought about it, you would never come up with the correct answer. Coming up with answers merely by thinking about things without using evidence, that's not science. It's called armchair philosophy. From the time of the ancient Greeks to the Renaissance, the public took what people in authority said as true, no matter what. It was inconceivable to people that Aristotle or the Bible were wrong about anything. That just couldn't be the case. The Bible says that the earth, with all of its seas and mountains and valleys, and man and all plants and animals, were created in 6 days. So there was never really a time before any of those things. Now, I'm not hating on the Bible for having bad science or anything. It's not a work of science. Nobody wrote or practiced any real science until only a few hundred years ago. For example, William Shakespeare wrote a play called The Tragedy of Julius Caesar, and historians don't go around criticizing that play for being historically inaccurate about the actual life of Julius Caesar. The play was not designed to teach you anything about history, and so there's no point in getting worked up about what the play gets wrong. Today, we know for a fact that Earth wasn't formed in a few days, and the animals alive on Earth today were not created, but instead they evolved. In fact, scores of different kinds of living animals have gone extinct. We take that for granted because of the work of countless scientists over the centuries. But without any proof, such as fossils, nobody would have thought, I bet 30-meter-long reptiles used to walk around and mountains take millions of years to form. So let's not look down on people from the past for not knowing and inventing stories. We are lucky enough to know more, but we didn't discover any of this. Other scientists did. Real quick, let me mention Aristotle again. Aristotle was wrong about pretty much everything. I mean, the guy thought that men had more teeth than women. But in his treatise titled Meteorology, which was an attempt at studying Earth system science and not just the atmosphere, he writes that the seas dry up, dry land becomes the sea, rivers don't flow forever, and even that the land rises and sinks, which is true, but he did not use physical proof to determine those ideas. The ideas simply seemed logical to him. That usually does not produce the correct answer. And even though he was right, he offered no explanation. If you can give a what, but not a how, that's not very useful. Okay, let's get on with the real science. The first true scientist I want to talk about today is Nicholas Steno. Steno developed several geological principles, but 5 in particular shaped the way we interpret geology rather than just observe geology. The first is the principle of original horizontality. This states that layers of sediment are deposited one at a time horizontally. Sounds like a no-duh kind of statement to us, but remember, back then, the majority of scientists and everybody else thought the world was only a few thousand years old. The mile-tall sequence of layers in the Grand Canyon, they thought, were not laid down one at a time. The entire geologic feature to them was one unit created all at once, and the fact that there are layers didn't mean anything. Next was the idea of lateral continuity. This fits directly with original horizontality, in that this principle states that layers of sediment extend laterally in all directions. So when we find continuous layers that are separated by a valley or other erosional features, we can assume they were once connected. You can see original horizontality and lateral continuity in Badlands National Park. Look how these thin pink layers extend perfectly straight across, and how you can find the same layers in front and far away in the back. This means that this landscape was not created looking like it currently does. Rather, all of these sandwiched layers were deposited, then much later, the majority of them were eroded away. Next is the law of superposition. In any sequence of sedimentary layers that are not heavily altered, each layer is younger than the layers below it, but older than the layers above it. Even in rock layers that have been altered, this pattern is usually not too hard to see. And again, this all sounds like a very obvious thing to point out, but this was a time when scientists were first considering that the many layers and geologic features on Earth were produced by natural processes, one at a time, slowly. Finally, there are the principles of cross-cutting relationships and intrusive relationships. These state that if some geological feature, such as an igneous body like a dike or a pluton, or such as a fault, intersects some rock layers, those structures are necessarily younger than the layers which they intersect with. You would probably like to see how all of this works, so I'll show you an example problem. If you're not interested in the example problem, then skip ahead to this point to resume the lecture. Here's a model of several of Steno's principles all at once from Wikipedia. We're going to go oldest feature to most recent feature. To find the oldest layer, always start at the bottom. In this case, it isn't actually labeled, but these tan and gray sedimentary layers that are heavily folded are the oldest. How do we know it isn't feature B? Because B is not also heavily folded, so it had to have formed after that event which affected the first layers. B is not the next layer either. It is the fault labeled A. This demonstrates Steno's principle of cross-cutting relationships. That fault has to be more recent than the layers it altered, but it is older than this feature called B because it does not involve that feature. Next up is B, which is an intrusive igneous feature. Next is actually this erosional line called an unconformity. The next oldest feature are these, yet again, unlabeled yellow layers on top. The reason we know B is older than these layers is that you can see that B does not intersect with these layers. B was eroded before those layers were deposited. Feature D, which is an igneous dike, is the next most recent, followed by layer E. The youngest overall feature is the fault labeled F. How do I know that fault is the youngest? Why couldn't it be the dike labeled D? They're not connected, so how do I know? Well, D is cut off by erosion before layer E, and layer E is moved by the fault labeled F. So that's how I know F is the youngest. The next important contributor to modern geology and understanding the Earth as a very old planet was James Hutton from Scotland. Hutton's most important contribution was the theory of Uniformitarianism. In simplest terms, it means that the Earth's features were shaped by the natural laws which we observe today. North America and Europe separate by about 5 centimeters a year on average. Okay, run the clock backwards and see how many years it takes at that rate to close the gap between North America and Europe. It turns out to be many millions of years, and we've already covered the many lines of evidence which confirm that. Erosion erodes away canyons, but it does so very slowly. Nobody has ever witnessed an entire canyon form before their eyes, so we can assume that the Grand Canyon eroded gradually, just as we see it gradually eroding today. You wouldn't look at a person and assume they were born the height that they are, even though you never saw them as a child. That's ridiculous. There are two opposing ideas with regards to uniformitarianism. The first one is creationism. Every human culture imagined how the world came to be. There are stories that Earth was hatched from an egg, or that Earth is the dead body of a fallen god or goddess. The oceans were formed from tears or blood, and so many other details and stories. Creationism accepts most of the observations we see today, like erosion, as being ongoing, true natural processes. They usually don't believe in evolution, though. But creationism does not accept the idea that the ongoing processes of today shaped the world of today. According to them, North America didn't separate from Europe. They were never connected. They just happened to be separating today for some reason. Creationism is still very common in the United States. A slightly more serious opposing idea to uniformitarianism is what's called catastrophism. Catastrophism states that Earth's natural features have been predominantly sculpted by sudden, short-lived, violent events. According to catastrophists, perhaps the biblical flood or something similar created the Grand Canyon and many other features. The reason the Himalayan mountains have fossilized seashells, to them, is because the entire mountain chain was thrust up into the sky from below the sea in a single day, not over the course of millions of years. So where does catastrophism come from, and why did people think that it was true? Catastrophism was used as a scientific argument for God and as a justification for what mythological stories say, at a time when the vast majority of people were religious and those ideas were considered to be unerring, which means they had to be literally true. But mythologies aren't scientific proof of anything. These types of arguments aren't scientific in any way. The problem with ideas like catastrophism is that you begin with your conclusion and then interpret evidence so that it supports your presupposition. That's not science. Wegener did not conclude that Pangaea must exist and then went out looking for evidence. He came up with the idea of Pangaea by following the evidence to its most logical conclusion. The illogical conclusions were the land bridges, floods, and coincidental erosion patterns. Let me be clear. Catastrophism is not a religious idea. Many scientists who were agnostic about the idea of creation still thought that Earth's geological features were created by catastrophic events. Hutton died in 1797, so he never saw his ideas become realized. But he was so far ahead of his time that he is considered the father of modern geology, much like Darwin is considered the first modern biologist. The person we will end with today, who popularized Hutton's work, is Charles Lyell. Lyell was born the year Hutton died, and was also from Scotland. Coincidence? Yes. Lyell went to great lengths to popularize and defend the idea of uniformitarianism, and an old, slowly changing Earth. While Lyell was a massively accomplished geologist, his most important work focused on stratigraphy, which is the study of rock layers. None of Lyell's major contributions would be new information at this point. Layers are deposited in sequence, their order determines their age, etc. But Lyell was a major influence and later personal friend to Charles Darwin. See, the fossil record preserved in geology also reveals to us that Earth's living things did not just show up on Earth one day, but they were shaped by ever so slightly modified generations of more ancient organisms. How the fossil record shaped our views of an old and slowly changing Earth will be the subject next time. Thanks for watching.